State two situations where a charged particle in a magnetic field does not experience a force. Why would you not experience a force? So, when you see questions like this, and if you're not sure how to think about it, ask yourself, when you have a charged particle in a magnetic field, for example, you need a force, but what is the equation for it? The equation for magnetic force generally is F equals to B QV sine theta. And what is the theta? The theta generally is the angle between the direction of motion, velocity, and of course B as well. Usually theta is 90 degrees because you know Fleming's left hand rule, 90 degrees apart. Okay, but do you want to look for when it's not having a force? So if you are already in a field, means there already must be a B. If you have a charge, you already have a charge. So the only thing that could possibly be zero is the velocity or the angle between not zero, sine theta, the angle between the B and the velocity. So if you look at the diagram on the left, if this particle is not moving, there is no force. But the moment it starts to move in the magnetic field, then only the force will appear and push this particle in. Use your finger, point at the screen, stick your middle finger out, upwards. Okay, upwards. So this particle experiences a force upwards, which while it moves to the right. Kind of strange. Okay, so let's mention that. So the first one, particle is stationary. Is stationary or not moving, then it will not experience a force. The second one is the direction, or rather the direction of velocity with respect to the B. So in this case, B is into the screen. There will be a force. But there's another case, I draw on the right side here. What if your B is pointing this way? Then you have a positive and you are moving this way as well. What's the angle between B and V? Zero. There is no angle between. They are parallel. So there will not be a force acting on this particle. It will just go along. That's it. So the second one you can say is the direction of motion, or you can say the particle is moving parallel to B. So particle is moving parallel to B. Okay. So there's 1 mark for each of these explanations based on the equation of force on particle. Then we come to this part 2. Now this is where things get a bit interesting. Here's a solenoid, also called a spring, and it's connected to a circuit. Okay, interesting. So electrical connections are made to the ends of the spring by means of a flexible lead. The length of the spring is measured, and then you close the switch. And then you measure the length again. So chances are the length of this spring, how do we say, unextended length, maybe something like this, will change whether you open or close the switch, because when you close the switch, there's going to be current flowing in this whole circuit, which is part of the spring. So what do we need to do here? First things first. When the switch is closed, a magnetic field is set up around each coil of the spring. Interesting. Magnetic field around each coil of the spring. By reference to each magnetic field, you know, each coil got its own magnetic field, to each of these, explain why there is a change in length of the spring. Whether does it extend or does it contract? So we need to talk about the magnetic fields of each coil, and then we explain why there's a change in length. And also I must mention whether extend or contract. So I think the first thing before we start off trying to write the answer is it going to extend or is it going to contract? Let's go back to this diagram. So this is what we call a solenoid. Usually we don't think of each coil separately, right? It's solenoid, right? If you have currents coming into the solenoid like this and then goes down to the next one like this and goes down, you can use your right hand grip rule and your fingers that curl follow the direction of the current, the orange color one that I just draw. So if I curl my fingers around this coil, my thumb should be pointing upwards. So if we were to draw the field of a solenoid, it would look something like this. Somewhat. You know, something like roughly like this now, okay? But the thing is, this is not helpful to tell us whether the spring will contract or not. we need to think of the hint here. Each coil, the magnetic field around each coil separately. So that means instead of thinking of a whole solenoid like this, we must say, okay, this is coil. Okay, no, let's draw on the right side. Coil number 1, or loop number 1, loop number 2, number 3, and number 4, for example. So let's see. Let's do a quick check. Will it contract or will it expand? Let's consider the one coil up there and another coil number 2 down there. Coil number 1, clockwise and then go in. Okay, that's a current. So if I curl my fingers around that thing, my thumb should be pointing upwards. So the field, if I were to draw the magnetic field, would be something like this. You say, Miss, shouldn't there be more? Yeah, there's more. Okay, let's draw more. So something like this. Okay. So this is kind of like a mini magnet if you ask me. The other coil down there, also the same thing. If your current is flowing in this same direction, you're also going to get a field pointing upwards. Like this. Okay. Based on this, I can already tell whether the spring will contract or extend. How do we know that? If you look at the solenoid on the left side, how do we know where it's north and south? You see, if you treat this whole solenoid as an electromagnet, remember what those are? This part is north, because that's where all the magnetic field lines come out, and this part is south. All goes into the solenoid, into our magnet. Okay, so that means, based on the idea, we look at each individual coil and treat it like a magnet. Yep, this one is north up here and down here is south. So it's kind of like saying I have a bar magnet like this, and also another bar magnet north-south like this. So will they attract or repel? You tell me, no? These two will attract because north and south, these south and these north will attract each other. So every single loop is attracted to each adjacent loop. And so the overall spring, once there's current going through them, they will compress. They will contract. Okay. We keep that in mind. Contract. So this is one method to get us thinking about it. But now we need to actually write it out. We need to explain by referring to the magnetic fields why there's a change in length. So we know it's going to contract. Let's put a check mark here. Okay. Let's talk about each magnetic field. So I'm gonna redraw those two once again, right here. Oh my, that is not a circle. That's more like it. Okay, so this, let's say coil number 1 will create a field thanks to a current flowing in it. So we got our field. I'm going to draw a few arrows. That's our B. That goes actually really far. So I'm going to draw all the field. And here you'll probably loop around and go out already. Like this. And curl around. Okay. Oh man, I erased everything. No, don't erase everything. Like this. Okay. So one coil creates a field. The other coil, if you are adjacent coil next to it, you will experience this fella's field. So let's say I am now at coil number 2. I am in somebody else's field, but I also have my own current. And the thing is, if you have current in a magnetic field, you will probably experience somebody's force. Right? Remember we mentioned, where will there be a force? When you have, when you are moving, which is charges, current, moving inside a magnetic field, perpendicular to the B. As long as you have this condition satisfied, you have a force. So we're going to use that same explanation here. And force, okay, so they attract. If you want to draw out the force will look something like this. This ring number 2, which is what we are focusing on, will experience a force pulling it towards the other coil, number 1. That's our direction of magnetic force overall. Okay, so let's talk about first things first. We need to mention the magnetic field because they say please reference the magnetic fields. So we can say that the each coil actually we only draw two here, but each coil, actually, they will experience a magnetic field thanks to their neighbors. So each coil is perpendicular. Or you could say the word normal. Normal also means perpendicular. I'm going to say perpendicular. So each coil is perpendicular to the magnetic field of adjacent coils. So the nearby neighboring coils. How do I know it's perpendicular? You see here, roughly in the middle. The sides, the effect kind of cancels out. But the middle mostly, especially if you're very close together, I drew them very far apart. But this is perpendicular. Okay, see they're very close. So that's number one. We talk about the field. Then, what next? Remember when you have moving charges, current is going to move left and right only in that plane, because it's a circular plane. Magnetic field is going to move up or down. So these two are going to be perpendicular to each other, at least in the middle. So number two, we're going to say that the current of coil will interact, current of coil will interact with the magnetic field. I am just lazy to write. I'm going to say B field due to the adjacent coil, the neighbors, and produce a force. To exert a force on the coil. And here we are referring to this force here because you have current in the field, so you have force. You can just talk about it like that. Don't worry so much about the left-hand rule, right-hand rule. If you want to use that, that's method number 2. We'll talk about that later. Okay, so we talk about the coil, the field that exists, talk about current and how there's a force. Now we need to mention this force is going to attract each other. So that's the diagram that we talked about just now here. North, south, south, north. North and south will attract. Use your right-hand grip rule. So let's mention that as well. So number 3, we are going to say that this force is attractive, number 1, and parallel to the axis or axis of coil. So they attract, number 1, and they're parallel. What is axis of coil? Now I see if I draw a circle, this coil, right? Axis is like this, So that's where your direction of force will generally be pointing towards. I just kind of drew at the side here because there's no space. Okay, next. Last thing, conclusion. So they're attractive. Alright, so the spring contracts. Because all the coils are attracted to all the coils and they all attract each other. If you want to draw that out, it's going to be a lot of arrows. I attract to you, you attract to me. I attract to you, you attract to me. I attract to you, you attract to me. And they all just attract each other and just go compact the whole spring. Okay, so the marks here, the first one is you want to talk about the magnetic field because they say reference the magnetic field. So if you talk about the magnetic field is perpendicular to the coils, that's 1 mark. If you say about if there's current in the field, there's a force, that's 1 mark along those lines. The third one is you talk about where is this force pointing. If you say use this method, the force is parallel to the axis or vertical or upwards, that is 1 mark. And the last one, attractive, therefore the spring contracts. That is the final mark. This is a very unusual question. Not seen this come up before in past years. So if you feel like, Miss, I have no idea how to do this the first time I see, it's okay. It's okay. We learn. All right. There is another method though. How to talk about this? The second method, you will see this also in the mark scheme, is a bit more tricky. It involves Fleming's left-hand rule. So I'm going to go over to a picture that I made, or rather a picture I found on the internet. Just Google and find. Okay, so this is method number 2 if you want to explain what's happening. This one is a little bit more strange. Okay, the first thing you want to mention, remember we mentioned the magnetic field lines. Okay, so you want to say that this field, you see these loops, it's actually a very circular field. If I were to draw the whole thing, it will go like this. It's a circular field except for maybe the middle line. So that's what it means by circular. So we got to mention that each coil has its own circular field. So number one, right here, B field around each coil is circular. So what does that mean? So when you have somebody else in this field, let's say this coil generates the field, and I'm going to put another coil like right on top here, I guess. Seems about right. Okay, because the spring, if you look at the picture, they're actually very close to each other. Now this, I have a current running through it. This is my current. Once again, you can mention if there is current in a magnetic field, you will experience a force. So we're going to mention that second thing, same as the point just now. So current in the coil. By coil, we are referring to this coil. So the current in coil interact with the B field to exert a force. Okay, because we got current, we got B field, we got force. Then, point number 3. This is where you kind of use your Fleming's left-hand rule. So if we look at the black coil on the left side, let's look at this point, like right here. The highlighted point. At that point, current is going into the screen. So I'm going to draw something like this. Because, you know, current comes out, goes in. Okay, I will change this picture a bit to make it a little bit more believable. Okay, so current is going into the screen. Magnetic field at that point, actually, if you assume it's kind of going to the right a bit, if you look at this part. So I'm going to say the magnetic field is kind of going like this, but for simplicity's sake, I'm going to say it's almost horizontal. This is the magnetic field line at that point, roughly. The angle will vary, I tell you first. Then because of this, you can stick your finger to the right. Point your middle finger into the page and you should get your thumb pointing downwards. Left hand rule. Yeah, something like that. So, because of this, we will have a force downwards on this coil. Can this one? Well, you say means in real life or this B is supposed to be tilted or? Sure, if the B is tilted a bit more, your force is just a bit smaller. But at A levels, we don't want to deal with that angle problem thing. But you will still be right angle, your force will just change direction, maybe a bit smaller. It will be like, let me see, your force will be a bit at the angle. Outwards a bit. Okay, but it's still the same thing, still somewhat downwards. That's the whole idea. Okay, so I'm going to keep it downwards for simplicity's sake. Let's check. What if I put another coil down here? And see what is the effect of this gold, orange color rings field on this coil down here. Same thing, we have current that's going to go in a circle and go behind all these field lines. Okay, so like this. What is happening at, let's say, this point? Maybe we should move down a bit more. Here lah. Make it easier on your brain a bit. Okay, there we go. What's happening? What's happening there? So at that point, current is going into the page. So we draw an X and go into the page. Magnetic field line is like this. So magnetic field line is roughly pointing to the left side a bit lah. So I think I might need to change my diagram a bit. So current into the page. Field line is roughly to the left, maybe upwards a bit like this. Somewhere there. And lastly, the force. So you got to use your finger, point to the left. Middle finger pointing at the screen and your thumb should point upwards. So this should be pointing upwards. Ooh, interesting. So this one orange color ring will pull the lower ring up and will pull the upper ring down. That's how you know attractive. How do you explain this in one sentence? You don't need to explain the detail. You just say a basic thing. You can say, like for a simplified case, the force is perpendicular, or you can use the word normal, to the coil and magnetic field. That's how you use your Fleming's left-hand rule, right? Force perpendicular to the coil, which is going to be represented by current, and a magnetic field. So all perpendicular, but only at certain spots. But we gotta simplify. If not, we cannot solve the question. Okay. And next thing is, so it's going to be attractive. So force between coils are attractive. Force between coils are attractive. So yeah, this is another method to think of it. I think this one is a bit more complicated because you have the problem of, Miss, what if this B is pointed at some funny angle? Granted, that's a legit concern, and at higher level physics, you will have to deal with them using vectors, but we do not want to deal with that, so we assume that it is this B, FBI is all going to be perpendicular, so we're good with this explanation. It's also a 4 mark. But I would recommend you know how to use this one as well. So yeah, both sides. Okay, let's finish up with this last part. So now we know the springs contract, got lots of forces happening there. With the switch closed, the small mass on the free end is now made to oscillate vertically. So you close the switch. Okay, wait. Let's do this. It's uncontract. You close the switch, it contract. Okay, now we are ready to do our experiment. So this one is already contracted. Now you made it to oscillate vertically. That means you pull the spring down and you let go. So it's doing a simple harmonic motion, almost. So you pull down, then you go low, very low down, then it will come to middle, then you'll go to high up, and you know, so on and so forth. I could draw a whole series of springs. It's going to follow your sine or cosine pattern. Goes up, goes down, goes up, goes down. Boing, wow, wow, wow. But we need to explain not the simple harmonic motion. We need to explain why there are small fluctuations in the current in the spring when you have this oscillation happening. How on earth does oscillation relate to electromagnetic induction? This is where you gotta think of the change in flux. Remember, this spring is connected to a circuit, okay? And you can treat each turn as a separate coil. So sometimes these two coils will be close to each other. Wait, let's make this very far away. Sometimes they are very close to each other. Sometimes they are very far. And you go like this, wow, 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 wow. Change in flux, change in flux, change in flux. Very strong field, very weak field. Very strong field, very weak field. So you get the idea. Okay, you get the idea. When it's contract, the flux is very strong. So when you say there's change in flux, somebody does not like the change in flux. Coils do not like change in flux. They will oppose that change. So let's talk about that. So the oscillating coils, we're going to treat each turn as its own coil. So oscillating coils cut the magnetic flux of their neighbors. Cut magnetic flux. If you want to mention this, sure. I'll just make a side note. This is due to adjacent coils. Or you can say there is a change in flux through each coil because they move closer together. Okay, so change in flux as separation of coil changes. What is separation of coil? From first coil to the second coil, they are at a certain distance apart, and they'll become closer, further, closer, further, closer, further. So that's your separation change or change in flux. This is the first point already. So you need to talk about induction. Change in flux, Faraday's law. So we're going to say this change in flux induces EMF in the coils itself. Or you say induce current. also can lah. But we stick to induced EMF. Because this one is related to Faraday's law, where you have an EMF which is proportional to the change in flux through a coil. So the next thing is, we'll talk about the current, because they ask at the end of the day, why are there fluctuations in current? Current, the idea is a current. So if EMF is induced, it's going to oppose. So change in flux induced EMF in coil that opposes change. So it will oppose whatever is changing lah. Okay, and the changing current. So the changing EMF causes a change in current in the circuit. Or I get to say in the coil. Very interesting, huh? Okay. Understand. So remember, as you're oscillating, the flux is changing through each coil. Just animate this, drag these two things closer and further together, you get what I mean. So there's 3 marks for this. The first mark, we are looking for the idea of, can you identify where is the change in flux? Oscillating coils, magnetic flux. So, or you can say the separation change as they move closer and further together. This one is B1. Number 2, you link together Faraday's law. Change in flux induces EMF in the coil. Number 3, I guess you could mention Lenz's law, but there's no mark for Lenz's law here. If they ask for damping, then you have to say, oh, it loses energy over time, oscillate until no energy. Then that one is, you have to mention Lenz's law. But here, the last point comes from linking together the changing EMF to the change in current, which is why there is a fluctuation in the first place. So your current won't be like a steady, although it's a DC circuit, you will not see a steady current like this. It will probably do a little bit of a wavy thing, like that. So some kind of fluctuation because of the induced EMF that opposes the change. Okay, I think that's all for this question. Kind of a tricky one. A very good one to really test our understanding of what are coils, magnetic fields, and even in oscillations. But that's all for this video. I will see you in the next one.